Worksheet solution for the problems in Chapter 7 worksheet. Problem number 1, notice I have a typo, proscribed instead of prescribed. A car with a mass of 1,054 kilograms is traveling along a road at V initial is 80 miles per hour when it reaches a warning sign that says there is road work 1 mile ahead and speed will be reduced to 40 miles per hour. The driver lets off the gas and speed is decreased to 50 miles per hour when she's just 100 feet from the 40 mile per hour sign. At that point, she applies her brakes to reach the prescribed speed when she reaches the 40 mile per hour sign. So she's going to be at 40 mile per hour in that 1 mile. If the elevation at the warning sign, the starting point, was 368 feet above sea level, and the elevation over all of the last 100 feet is at 122 feet above sea level, how much work was done by air resistance and rolling friction combined? We're taking those as one thing, not separating them out, while her speed was dropping from 80 miles per hour to 50 miles per hour, and how much force did she need to apply with her brakes at the end if the work done by air resistance and rolling friction over the final 100 feet is negligible? What was the average power of the wind resistance and rolling friction? Once again, that's one thing. And what was the average braking power over the final 100 feet? Assume that all numbers are good to 3 significant digits and acceleration was constant in each region. So what's the concept? It seems pretty out there, right? You could try to solve this problem using Newton's second law. It doesn't ask you for accelerations. It does say assume constant acceleration. And so you could use Newton's second law, but it would be a bigger problem. It's easier to do the problem using the work-energy relation. And so that's what I'm using for my concept. Right, so when you're doing this, if you were doing this on the test, you could have said Newton's second law because nowhere did it say you had to use energy in the problem description. Now, in my work below, I assume you're going to use the work-energy relation, so the leading tells you to use it. Draw a diagram of the problem. It should show all 3 locations mentioned in the problem. So here we go. Starting point, the place where she starts braking, and the ending point. Write out the equations for kinetic and potential energy at each of the 3 locations mentioned in the problem. So I have here initial kinetic energy is 1/2 mass of the car times initial speed squared. Initial potential energy is mass of the car times g times the initial elevation. The kinetic, I gotta change colors, too much blue on this. Kinetic energy at the point where she's 100 feet from the end, 1/2 mass times, I called it 1, so speed 1 squared. Potential energy 1 is mass times g times elevation 1. And then in the final case, kinetic energy final, 1/2 mass times v final squared, but she comes to 40 miles an hour. She's not at rest. That's it. Potential energy final equals mass times g times y final. So there I have the kinetic and potential energy equations. Put a box around each set just so that they stand out at each of the locations. Remember, when you're doing work-energy relation problems, that's your starting point. Find the kinetic and potential energy at each location. Then I generally say, determine if there is non-conservative work, and if so, calculate it. Now, in this case, yes, we're told there's air resistance and rolling friction non-conservative work for the forces for the first part, and then there's braking non-conservative force, conservative force for the second part. So we have non-conservative forces in both cases. However, our job is to find those non-conservative forces based on the numbers given rather than to use the non-conservative forces to find the speed or whatnot. So here I have a table for writing out the equation. So potential energy at the start is mass times g times y initial. Potential energy 100 place, the final place, kinetic energy, right? That's just using those equations, not very tough. Now a bunch of unit conversions. Starting speed of 80 miles per hour. Well, 80 miles per hour. So 1 mile needs to be on bottom. I need meters on top. So I put MILE. Usually we just put MI for mile to cancel those units. So how many meters are in a mile? Well, some of you will remember 1609 meters in a mile. I sure hope that's right. That's what I remember. Let me just double check my conversion there. Yeah, I just used the full-on thing. And then I have hours. Hours are on bottom, so I need hours on top and seconds on bottom because that's the standard unit. So 1 hour is 3600 seconds. And so if I have 80 multiplied by 1609 divided by 3600, I end up with 35.76. And if you put that in the calculator and you get a different number, it's because my 1609 is going from memory. So that's 35.76 meters per second. And then I'm going to put one more digit on there, or two more, just so we don't have any option round off errors. Doing the same calculation with 50 miles per hour gives us 22.352 meters per second. And 40 miles per hour gives us, of course, half of what we had for 80, 17.8816 meters per second. Now for the elevations, my starting elevation was, I'll change color just because we're doing a different type of calculation, 368 feet. And then, how do we do conversion from feet? Well, here's the way I do it because I'm a moron. I know that in 1 foot, there are 12 inches. And then I know that in 1 inch, there are 0.0254 meters. Exactly. So that's an exact conversion factor. That's what I do. It's more steps. You could look it up and find it with less steps. So when you multiply that through, it turns out to be 112.1664. And then the final at 122 feet, doing the same calculation, gives you 37.1856 meters. So I have the elevations there in terms of meters. And then finally, my distance is 1 mile. Well, this is going to make you really laugh at me. No, 1 mile is 1609 meters. I was going to do the 1 mile this way just to start with feet. So that should be 1609 meters. And delta x, the distance of 100 feet, by the same method as we did for the other feet, gives us 30.48 meters. So there I've done just a whole bunch of unit conversions because I gave you all kinds of wacky units in this. Why did I give you those wacky units? Because those are the units that we most often use in our daily lives, not in physics ever, but in our daily lives. So now calculating the potential energies and kinetic energies at each location, just putting in the numbers. So putting in the mass, remember mass is 1,054 kilograms, G 9.8 meters per second squared, and the elevations. Then you get the potential energy at the start is now, of course, that has ridiculous non-significant digits in it. The reason I'm putting all those out is, again, just round off error issues. This is 0. And of course, since the elevation for 1 and final is the same. erase that and make it more like this. And then kinetic energy is 1/2 mv squared. It's 674,036. And that 0 looks wrong. 26, 95.5, 168, 509.1. So there I calculated all of those potential and kinetic energies because I could, because I had all of those values. Now apply the work energy relation between the start and the 100-foot point to find the work non-conservative for the first stretch. So I have work non-conservative is equal to change in kinetic energy plus change in potential energy. So that's equal to going between 1 and 0, 263295.5 joules minus 674036.4 joules. That's my change in kinetic energy plus my change in potential energy. Can't see those at this point, but I've got them on a computer screen. 384097.5 joules minus 1158589 joules. Notice actually both of those are negative. The kinetic energy decreased and the potential energy decreased. And when you put it all together, you find that's equal to minus 1,185,233 joules. Now that's it. How many significant digits do I have there? Like 3, so it's 119. I'm going to put this in scientific notation, so minus 1 point, I'm going to put 185 times 10 to the 6th joules. Negative, because we lost that energy. Apply the work energy relation over the final 100 feet to find the work done by braking. So now we just do the same thing. Work non-conservative 2. So that's going to be final kinetic energy, 168,509.1 joules. Minus the intermediate one, 263295.5 joules. Plus the change of potential energy, which is 0 because these are the same value. So I didn't write that out because it's just a bunch more writing that it might say. So doing that calculation, it gives me minus 94786.4 joules. It's 479 times 10 to the 1, 2, 3, 4 joules. Use the equation for work to determine the magnitude of the force of friction over the final 100 feet. So I'm going to have work non-conservative 2 is equal to force of friction dotted with delta x. Force of friction, we're looking at that car. It's going this way. Delta x is thus that way. But force of friction is that way. And so force of friction, delta x, are 180 degrees from each other. Cosine of 180 degrees is minus 1. So I have my work non-conservative 2 is equal to minus the force of friction delta x. Divide both sides by minus delta x. I have force of friction equals minus work non-conservative 2 over delta x equals minus parentheses minus 9.479 times 10 to the 4th joules over delta x is 30.48 meters. Notice there's a minus and a minus, so the minus and a minus is going to make it positive. And that gives me a force of friction of 3,110 newtons. So that's how much friction had to be applied. Moving on, power is defined as the work over time, or force times speed, force dotted with speed, because those are vectors, that's a dot product. So we either need to find the time for a period along with the work, or the average force and average velocity. We already know the works for both periods along with the average force for the second period. To cover both options, you'll calculate the time for the first period, even though it's a harder method, and the average speed for the second period. For the first period, use the appropriate kinematic equation to find the acceleration. So for the first period, I have the speed at the beginning of the first period is this, and the speed at the end of the first period is this. And I have the distance that it's traveling is, 1609 minus 30.48. So I can calculate I don't have time, right? So I'm going to want to find the equation for the acceleration, distance, speed, and no time. So that equation is acceleration 1 is equal to v1 squared minus v initial squared all over 2, and my distance is d minus delta x. That's 1 mile minus 100 feet. So that's equal to v1. Speed 1 was 22.252. Squared minus initial speed of 35.763 meters per second squared all over 2 times my 1609 meters minus 30.48 meters. And that gives me A1 equals, I'm just going to make sure I was making sure my calculation was correct here, gives me minus 0.2469 meters per second squared. Using the starting and intermediate speeds along with this acceleration, use the appropriate kinematic equation to calculate the time she was coasting. So now I'm looking for time. So I'm going to have change in speed, v1 minus v initial. Now let's just do it before I start. Oh, don't know what happened there. So I'm going to take my v1, 22.352 meters per second, minus the initial, 35.763 meters per second, divided by the acceleration, minus 0.2469 meters per second squared. And I find that time 1 is equal to 54.324 seconds, which totally makes sense because you take just under a minute because your average speed is just a little above 60 miles an hour. So that is 54.3 seconds. Using this time and the work done by air, resistance, and rolling friction in this problem to calculate the average power. So power average is equal to work over time. And so that work was minus 1185. This is scientific notation. Minus 1.185 times 10 to the 6 joules over 24.324 seconds. And you get the power average is equal to minus 21,818, but 800 watts. So that's the power from the rolling friction. And then we want to calculate the power from the braking. And this time we're going to find the average speed and do force of friction dotted with speed. So the force of friction, we already know. The average speed, V2 average, is equal to V1 plus V2 divided by 2. So that's going to be 45 miles an hour would have been easy, right? But no, we have to do it in meters per second. So that's going to be 22.352 meters per second plus 17.88.6 meters per second all over 2 equals an average speed of 20.1168 meters per second. Now, calculating the power this way, power average 2 is equal to force of friction dot V average 2. And so once again, the V average is forward, the force of friction is backwards, so this is going to be a negative value. I'm just going to put in magnitudes and put the minus sign out front. The force of friction, as calculated earlier, was 3,110 newtons. The actual value is, well, that's close enough. And then the average speed, we just got 20.1168 meters per second. And we have the average power is minus 62559 watts, or minus 626. Minus 6260 watts. So there we have done a problem that involved calculating work energy things and power. A work energy chapter makes sense. The final question for this section is about, again, energy, clearly, but we're now dealing with a waterfall. That is the Niagara Falls. I tried to get as accurate of values as I could for this. I found some conflicting numbers, so this may not be right. But the Niagara Falls, on the U.S. side, we have 567,811 liters per second that go over the falls. Much more water than that is diverted into the 2 power plants. And the falls themselves have a height of 53.6 meters. The Canadian side has about 4 times more water that goes over it. So the 2 American power plants are currently producing 2.7 gigawatts of power, and the 3 Canadian power plants are producing 2.2 gigawatts. They have positioned those so that they are higher on the stream with dropping the water to a low level, so they have a bigger change in elevation, hence a bigger change in gravitational potential energy of the water from on top to the bottom. Now what we are going to do is we are going to calculate how much more hydroelectric energy could be created if we have the water is basically still at the top and basically still at the bottom. And it flows in and flows out at the same speed. And we just convert the potential energy into electricity. And we're going to assume the density of the water is that of pure water at 4 degrees Celsius, which is 1 kilogram per liter. So the first question is, what's the concept involved here, right? I mean, the problem seems pretty drawn out. But the concept involved is going to be, again, work energy relation. Now draw a side view diagram showing the river flowing into the hydroelectric plant and then continuing flowing out of the hydroelectric plant. So we have water flows in and then it goes, so actually we're going to have just a big pond here, if you will. And then we have, here's the hydroelectric plant, has a vertical drop. The water comes down. goes through some turbines, and then comes out. And so there's our basic picture. We have a change in elevation. I'll just say the top height is my 53.6 meters. The bottom height is 0 meters. So I set my reference point at 0 at the bottom. And I also have the flow rate. And the flow rate is Q is actually a symbol we use for. We haven't learned that yet. 567,000. Wow, I got that right. 811 liters per second. Now, the technical abbreviation for liter is a lowercase l. I often use an uppercase L, and you'll see other places use that as well. We can immediately convert that into a mass flow rate. We still call it Q, confusingly enough. So this is the volume flow rate. The mass flow rate is going to be that Q volume flow rate multiplied by the density of the water. But the density of the water is 1 kilogram per liter. So that's going to be the same number, 567,811 kilograms per second. So there's our picture. Since power is energy transformed per time, and we're given a flow rate, which is volume of water per time, which we now have converted to mass per time, we do all our calculations by dividing by time. So we're actually going to take that work-energy relation, and we're going to say, well, I put it down here. That's what we're going to do, is just divide everything by time. And so I want the change in momentum, or change in potential energy per time. So I just put the potential energy initially is mass times G times Y0, and I put over delta T. And finally, it's mass times G times Y final over delta T. But mass over delta T is my mass flow rate. So there I have found the power in and the power out, if you will. And they both depend on the flow rate Q, G, and of course the elevation. So since the power is defined as the difference in these two, I'm just going to take the power output is equal to Pn over delta T, so Q, G, Y0, minus the out, Q, G, Y1, or making it easier, QMG times Y0 minus Y1 equals, and then I just multiply the numbers, so QM was 567,811 kilograms per second. Multiply that by 9.80 meters per second squared, and I didn't give myself enough space, so continuing down below. The Y final is 0, it's the Y initial minus Y final. The Y initial is 53.6 meters minus 0. So if I multiply all of those through, then I get a value of 2.98 times 10 to the 8 watts, or 298 megawatts. So I'm going to put 298 megawatts. Make sure it's a capital M, doesn't look like a lowercase m. In the U.S., our average electrical power consumption is 1,377 watts per person. That's 11th highest in the world. How big of a city could be powered by the American side of Niagara Falls? So I'm just going to take this value, 298 times 10 to the 6th watts divided by 1.377 times 10 to the 3rd watts per person. And that gives me 216,600 people, or rounding to correct sig figs here, 217,000 people. Now, in actuality, of course, they would divert that water back to the higher power plant. They would get more energy out of it. But it gives you a good rule of thumb for putting in a power plant. Now, the rest of this question is dealing with important ideas of responsibility. The worldwide average electrical power consumption is 309 watts per person. We're way above that. Why? Well, there's easy answers and there's harder answers. The easiest answer is we're greedy here. We're very wealthy. We are, lots of money. The poorest people in the United States would be considered wealthy if we're talking to homeless people in the United States, would be considered wealthy if they were in Europe, believe it or not, just based on the amount that they consume, the amount of money that they spend. They don't live as nicely as the wealthy in Europe by far, but that's because we are wasteful. So, that's the first answer. But then if you analyze a little more, you also come to realize that Canada uses even more. Why the Canadians use more? I think there's an obvious answer. The Canadians are farther north. It gets colder up there. And so they have to use more energy for cooling. The greatest use of electrical power in the world is Iceland. Well, that makes it clear, right? Very cold. Got to use a lot of energy for heating. And the lowest is the Gaza Strip at only 0.01 watts per person. That's a political situation there, right? Those are people that are being repressed by a government, and so it's a tough life there. Chad is only 1 watt per person. What does that tell you about Chad? Chad is a fairly undeveloped region. They don't have much electrical infrastructure. It's not available to people. So, of course, they don't use much. So, overall, we need to be responsible, I believe. God has put us here to care for the earth, and that means to be responsible about the assets that we have, our energy resources. And just throwing away willy-nilly, doing things like, this drives me crazy, I'm an old man, I guess. You have the heater on when it's cold outside, and yet you leave the front door open. Well, that's a lot of excess energy that's being wasted. And I don't fault you for heating the house when it's cold or for cooling the house when it's hot. I do that myself probably more than I should. But we also need to make sure that we're not just throwing it away or doing things like leaving the refrigerator open when you have the air conditioner on. The air conditioner, of course, is cooling the house. The refrigerator, as we'll learn later on this semester, is a net heater. And if you leave that door open, you're just spending electricity to heat the house and then have the air conditioner cooling the house. So we need to be responsible about this. And that's the reason why we have legislation to try to move Americans from incandescent light bulbs, of which only 5% of the power of the energy that we use in a light bulb, in an incandescent light bulb, goes into lighting. The rest of it goes into heating. So those light bulbs are much better heaters than they are light producers. If you change to a compact fluorescent or an LED, then about 1/3 of your energy is going into light, which sounds horrible, but still 6 times better than an incandescent. So you're saving a lot of energy by using the LED or the compact fluorescent light bulbs. And if those compact fluorescent light bulbs were actually reliable, I think they would have taken off, but those things just aren't reliable. Okay, so hopefully you've learned something and you've thought a little about the responsibilities we have.